In the last episode, we considered the simplest distortion effect scheme, which produces a fuzzy-buzzy sound. Today I will show you how to correct the tone of the device using filtering. Additionally, we will listen to how the distortion character depends on the equalization of the previous stage. One of the most important factors that influence our perception of music is the frequency balance. An old-school tape recorder with saturated bass and mid-range sounds can give us a warm and nostalgic experience. On the other hand, new bass-boosted car-oriented music can bring us to a rush drive consciousness. The Marshall GCM series and Mesa rectifier are two completely different sounds, not only in terms of the amount of distortion, but also in their timbre. There are several basic types of filter, and each filter has its mirrored copy. Therefore, filters can be grouped into pairs of twins. The first pair is the high-pass and low-pass filters. This type of filter has one parameter, the cutoff frequency. For an ideal low-pass filter, a signal with a frequency less than cutoff frequency passes through it without attenuation, while a signal with a frequency higher than the cutoff frequency is fully absorbed by the filter and does not pass through it. Conversely, a high-pass filter cuts the lower frequency signals and allows signal with the frequencies greater than the cutoff to pass through. A real filter does not fully absorb the cut part of the signal. It attenuates it, and the amount of attenuation for each frequency depends on the filter design. The simplest filter of the first order has a sloped frequency response curve compared to the step function of an ideal filter. The point at which the signal is attenuated to the square root of 2 times or equally -3 dB is the cutoff frequency point. The slope of the graph shows that the signal is attenuated twice per frequency doubling. Filters with a higher order have a steeper slope, resulting in a greater attenuation of frequency above the cutoff point. Here is an example of my voice and my CNC machine sound recorded with a high-pass filter with a cutoff frequency of 250 Hz. Now I will adjust the filter to 150 Hz. The high-pass filter removes noise and adds clarity to the signal, but it also results in some loss of information. Next, it is example of my voice and pepper rastal. I set up a low-pass filter with a cutoff frequency of 1.4 kHz. This filter cuts off the details of the sound. If I decrease the cutoff frequency to 600, you can hear the reduction in detailization, creating an underwater effect. However, this reduction draws the listener's attention to the central tone. The next twin pair of filters is the notch and bandpass filter. They are a combination of high-pass and low-pass filters. Notch filters reject only a specific part of the signal's frequencies, while its twin brother, the bandpass filter, passes a narrow part of the spectrum. These filters have two variants of parameters, either two -3 dB frequencies low and high, or a center frequency f0 and quality factor, which represent the width of the filtered band. There is a relation that binds these parameters. The last type of filter is the shelf filter. It's similar to the high-pass and low-pass filters, but they attenuate the signal to determined value. Shelving can be used for the redistribution of frequency balance and can be applied as a booster or attenuator for a certain frequency range. It's characterized by a lower frequency, upper frequency, and gain factor for shelves. I use a 5 dB shelf filter for my voice in records to boost the bass. Without this filter, my voice sounded less expressive and colder. This is a common trick for speech recording. Sound equalization is achieved by a combination of filters. They are needed to find a balance for tone depth, clarity, detail, and noise. This balance may be very different for various sound production tasks. The simplest filter circuit consists only of the resistor and capacitors. This type of filters is called a passive filter because its maximum gain value is equal to 1, meaning it can only attenuate the signal. In an experiment, if we apply the AC signal from the generator to the input of this circuit, we can observe an interesting phenomenon where the capacitor conducts the signal. On the 430 Hz frequency, the amplitude is 1.5 volts. If I double the frequency, the amplitude will be 2 volts. When we increase the frequency of the generator, the amplitude of the output signal also increases. We can view this circuit as a voltage divider, with one of the resistors replaced by a capacitor, frequency-dependent voltage divider. From the previous episode, we know that the voltage divider has a gain function corresponding to the formula. As a result, we can conclude that the capacitor has a characteristic similar to the resistance, with several peculiarities. Firstly, this characteristic depends on frequency, and secondly, this is not real resistance, because capacitor does not dissipate power. This characteristic, named reactance, signed as X. For the capacitor, it inversely proportional to frequency and capacitance, where omega is angular frequency equal to the frequency multiplied by 2p, and the gain factor of the represented scheme depends on frequency. The key to intuitive explanation of this phenomenon can be found in the previous episode, where I showed the curve of the capacitance charge process. If we consider a graph that represents the dependence of the amount of the capacitor charge, Q, over time, we can understand the behavior of the capacitor in the circuit. When an AC voltage is applied to the circuit, the capacitor charge and discharge in a cycle. In the graph, the green curve represents the charge process for a large capacitor, while the red curve represents the process for a small capacitor. The current through the capacitor is limited by the resistor. As a result, both capacitor has the same amount of charge. However, the larger capacitor, which had a higher capacitance, will have lower voltage. This is clear from the expression for the capacitance. If both capacitors have the same current but different voltage level, it means that they have different impedance values. The complex impedance of the circuit, consisting of resistance and reactance elements, is a complex number Z equal R plus Jx, where J is the square root of -1. The visual representation of complex impedance is a vector with the x-coordinate corresponding to resistance and the y-coordinate corresponding to reactance. The complex impedance of the circuit from the experiment can be visualized on diagram. Since complex impedance is a vector, not a scalar, we need an abstraction that allows us to use 2D vectors as scalars. This abstraction is provided by a complex number. If you are not familiar with the complex numbers, you can watch a playlist about complex number by Welch Labs. The link is in the description. However, for our purpose, we only need two formulas represented on the screen. Where Z star is a complex conjugate, we just replace the sign and reflect Z across the real axis. Complex numbers are widely used in the signal processing and electronic engineering because one value can contain information about the amplitude and phase of the signal. If you want a deep dive into this topic, leave a comment. We can operate with impedance similar to common resistance, and the formula for the series and parallel circuit has the same form. I believe you recognize the circuit diagram used in the capacitor impedance experiment. we can calculate the formula for the cutoff frequency of this circuit, which is similar to the calculation for a voltage divider. The current flow through the capacitor and resistor is equal to the input voltage divided by the impedance. The underlying indicate that we are using values in the frequency domain. Underline U is a complex number that contains amplitude and phase of the signal. The voltage on the resistor, which is also the output voltage, is equal to the calculated current flow times its impedance. Similar to the voltage divider, we have a gain function. Dividing the numerator and denominator by R, we get expression. By multiplying to the complex conjugate, we get the expression for the square of the gain, and the final formula for the ordinary gain factor. From the gain factor formula, we can calculate the cutoff frequency. By definition, this cutoff frequency is the point where the attenuation equals square root of 2. After some algebraic manipulation, we obtain the formula for cutoff frequency. The analysis of the expression for gain reveals that the gain is 0 at 0 frequency, and at infinity frequency the gain equals 1. Based on this analysis, we can conclude that the scheme functions as a high-pass filter. First-order RC high-pass filter consists of a resistor and capacitor connected in a series. The capacitor exhibits high impedance for low-frequency signals and easily conducts high-frequency signals. The attenuation decreases with the frequency. Cutoff frequency, where attenuation equals square root of 2, can be calculated by a formula. If we swap the resistor and capacitor in high-pass filter, we obtain a low-pass filter. The cutoff frequency for the low-pass filter can be calculated using the same formula as the high-pass filter. In this circuit, the resistor can conduct all frequencies, but the capacitor shunts high frequencies to the ground, thereby allowing only low frequencies to pass. A band-pass filter allows a certain range of frequencies to pass through while rejecting other. It's achieved by combining a high-pass filter and a low-pass filter. If the resistance and capacitance value of both halves are equal, then the formula for central frequency remains the same. However, it's important to note that the maximum gain of the circuit is 1/3. A notch filter is also known as band-stop filter. It can be realized using a Wien bridge or a twin T filter. The twin T filter consists of two symmetrical T filters, which are variation of low-pass and high-pass filters with distributed resistance or capacitance respectively. The narrowest notch filter has a specific element ratio shown in the circuit diagram. The central frequency of the notch filter has an additional divider in the formula because the design requires zero gain at the cutoff frequency, which demands a doublet value of components for the upper low-pass filter. The Q factor of the passive filter cannot be larger than 0.25. To achieve a larger Q factor, an active design is necessary. Shelf filters are a type of frequency filter commonly used in audio applications. They are similar to low-pass and high-pass filter, but with an additional resistance element that limits the amount of attenuation. In the high shelf filter, for frequencies lower than the cutoff frequency, the resistors R1 and R2 work like a simple voltage divider. For frequencies higher than a cutoff frequency, the attenuation is limited by the value of R2. Similarly, in the low shelf filter, R2 limits the attenuation at high frequencies. The previous version of the distortion schematic sounded redundantly fuzzy because it does not have a tone shaping circuit. To improve the sound, we can modify it into two ways. Firstly, we need to adjust the gain stage so that the low frequency gain is much smaller than the high frequency gain. This is important because harmonic saturation of the sound in the clipping stage depends on the input amplitude, and limiting low frequency saturation will prevent the rich harmonic spectrum of oversaturated bass from the overlapping with the main tone of natural string harmonics and the other sounded strings. Secondly, we can add the low-pass filter after the clipping stage to reduce noisy scent from the sound. This scent is a cacophony of high-order harmonics produced by a clipping stage. Let's return to our gain stage. To reduce low-frequency saturation, we can use the shelf filter instead of voltage divider in the feedback loop. However, it's important to determine the type of the filter. It's worth noting that the frequency response of the filter is different from that of an amplifier. To understand the relationship between them, we can plot the frequency response of the amplifier based on the shelf filter frequency response graph. In the frequency range from 0 to f1 for shelf filter, the gain value is equal to 1. Which means that the op-amp has 100% negative feedback and behaves like a buffer. For frequencies greater than f2, the amplifier has a constant amplification factor determined by the voltage divider formula. The slope region between f1 and f2 smoothly amplifies the input signal. It may not be immediately obvious. We can achieve a high-pass frequency response by using a low-pass shelf filter in the feedback loop. This is the actual gain stage schematic. The potentiometer RP sets the gain and F2 frequency simultaneously. That's allowed to move up a shelf plateau. Meanwhile, the resistor R1 defines the maximum gain value and R2 sets the minimum gain value. The capacitor C defines the frequency response of the gain stage. Let's calculate. The typical gain range for distortion overdrive effects is between 215 and 800. The shelf filter F1 frequency value is set to the inaudible range, while the cutoff frequency F2 corresponds approximately to the highest guitar note at 1.2 kHz. For R3, I've chosen a value of 680 kΩ, and for R2 a value of 2.2 kΩ, which yield the maximum gain equal 310. To calculate the capacitance value for the low-pass filter, we can use the already known formula. It's important to note that the capacitance value is only a reference and we can increase it for a full-bodied sound or decrease it for sharper, more shrill sound. In another modification, I introduced a capacitor after the clipping diode. The output impedance of the voltage divider, which consists of resistor and diodes, is equal to parallel circuit, where RD is a dynamic value that varies with applied voltage. In our last episode, we explored the IV curve of the diode and how the slope of tangent determines the diode's resistance. When the diode's voltage is small, its resistance is very high, and the output resistance is mainly determined by R. However, as the diode voltage increases, its resistance decreases, and the cutoff frequency of the filter also decreases. As a result, we have a dynamic filter that attenuates many high harmonics when distortion is high, and only attenuates a small portion of high frequencies when distortion is low. This means that the filter's cutoff frequency adjusts itself based on the amount of distortion, resulting in a more tight-sounding effect. We only determine the order of the elements' values based on the desired frequency response. However, the final selection of element values ultimately relies on a subjective evaluation with the help of a precise tool, our ears. For the clipping stage filter, I calculate the capacitance value for a 3.5 kHz cutoff frequency, which corresponds to send range of the sound. Using the formula for a low-pass filter, this capacitance is equal to 4.5 nanofarad. The final modification involves placing the regulated shell filter after the buffered clipping stage. We buffer the clipping stage to shield it from the Tonestack resistance influence and vice versa. This shell filter can regulate the amount of high frequency. You can calculate the parameters of filter yourself for two different positions of the potentiometer. The volume potentiometer has a little effect on the Tonestack because its resistance is significantly greater than the previous circuit resistance. Let's start testing the sound with the filters. I add the capacitor to the feedback loop. Clipping stage still without the capacitor. Do not pay attention to the high frequency sound. Concentrate on the bass and mids. Now I add capacitor to the clipping stage. This capacitor must work as the sand hoover. Frequency balance device better than the flat fuzz from the previous video, but to be honest, I don't love the sound of the paired diode distortion. Too many even non-linearity products, the long harmonic spectrum. I'm starting this series of video to demonstrate a schematic that produces sound without annoying harmonics. In the next series, we will explore nonlinear wave shaping and how different types of diodes and transistors can affect the signal distortion. And finally, you get the first applicationable variant.